So, we have already studied some properties of random variables, or rather the sequence of random variables when n goes to infinity. So, most important theorem is, or the results in this field is the central limit theorem, which is basically related to the distribution in which a sequence of random variable converges, or rather a sequence of random variable converges to another random variable, which is called in distribution. That means, we are interested in the distribution of the sequence of random variables, and we also look at the distribution of a particular random variable, which is in fact the limiting random variable. Now, today in this during the next 20 minutes or so, we will extend this idea in order to develop another result, or another extremely important result for a multivariate distribution, which we call multivariate central limit theorem. Now, it is quite natural that this multivariate central limit theorem should evolve from the same notion, or maybe from the same theory, or maybe from the same approach or idea of the central limit theorem for a sequence of univariate random variables. So, now we are going to present this multivariate central limit theorems, its characterization as we along with proofs. The main objectives of this talk can be summarized as first, we will give statement and the proof of a famous theorem of that relates to this central limit theorem, which is known as Cramer-Wald device, and which leads to a different which leads to a multivariate CLT, although, but later on we will give you a version of a more general multivariate central limit theorem. So, let us start with the Cramer-Wald device. If I call this as a theorem, the statement of the theorem goes like this. Let x n be a sequence of random vectors in R k. R k is a k dimensional Euclidean space. Then x n converges to a random vector x if and only if each linear combination of the components of x n is a vector. So, each linear combination of the components of x n converges in distribution to the same linear combination of the components of x. So, if we consider a particular notation, the sequence of random vectors x n, this converges to x in distribution if and only if L prime x n converges to L prime x in distribution for every L. Now, it is very clear that L prime x is univariate, because it is a linear combination of the components of x. So, this theorem essentially gives a characterization of the central limit theorem with respect to random vectors in terms of univariate random variables. So, this is extremely important, because whenever we come across anything that relates to multivariate or random vectors, we can immediately transform it in terms of univariate functions or random variables, and then again go back to the multivariate part, which we will demonstrate later on also. So, let us start the proof, and as we know that the distribution function and characteristic functions have actually one-to-one correspondence, that means characteristic functions defines the distribution function uniquely. So, we start with deriving the characteristic functions. So, let x n, which is a random vector having components x n 1, x n 2 up to x n k, and let x be another random vector having components x 1, x 2, x k. So, the corresponding characteristic function of x n is phi n, and characteristic function of x is phi. Now, choose any real variable L vectors, real vector L having components L 1, L 2, L k. Then L prime x n is naturally L 1 x n 1 plus up to L k x n k. Now, this converges in distribution to L 1 x 1 plus L 2 x 2 plus L k x k equals to L prime x. So, first we are assuming that central limit theorem holds with respect to the univariate random variables. Then by continuity theorem of characteristic function, we can immediately write that phi n of T L 1 comma up to T L k goes to phi of T L 1 up to T L k as n goes to infinity, and this is true for all t. This for all t is extremely important. Since it is true for all t, we can just put t equals to 1, and we know that since L1, L2, Lk are arbitrary, then the entire proof follows from multivariate version of continuity theorem, because we are observing that the left side is the sequence of characteristic functions for a sequence of random vectors, and right side is the characteristic function of another random vector, that is, in this case it is x equals to x1, x2, xk. So, by uniqueness theorem of continuity theorem of multivariate version of continuity theorem, we can immediately say that x n converges to x, which is a random vector in distribution. Now, naturally converse can be proved by exactly similar arguments. We assume that x n vector converges to x vector in distribution, and then we write down the characteristic function of these vectors, and since this is convergent, from there we can go on to create a linear combination of this sequence of random vectors, which essentially converges to a sequence of converges to a particular random vector in terms of univariate random variables, which is a function of the components of the random vector. So, the proof is extremely easy, because we have used characteristic functions, especially two important properties of characteristic function. One is continuity theorem, another is uniqueness property. Let us discuss a particular use of this Cramer-Wald device. Show that, suppose this is a problem, show that x vector is multivariate normal if and only if L1 x1 up to Lk xk is univariate normal for every real L1 L2 Lk. Now, it is very important to we should emphasize always that this for every real L1 L2 Lk. If this thing happens for a particular or a few particular values of the choice of L vector, then this might not hold true. Again, we use the characteristic function of these vectors and variables. So, characteristic function of random vector x is phi of u1 into uk, which is expectation of e to the power I u1 x1 up to I uk xk. Since y equals to summation uj xj is univariate normal, then the characteristic function of y is exponential I tu minus half t square sigma square, where mu is expectation of y, which is nothing but summation j equals to 1 to k uj into expectation of xj, and sigma square is variance of y, which is nothing but double sum or single sum over ij both equals to 1 to k ui uj into covariance between xi and xj. Now, again, as we did in case of Cramer-Wald device, just put t equals to 1 and we put and define mu j as expectation of xj, sigma ij as covariance between xi and xj. Then we immediately get phi of u1 u2 uk equals to e to the power I into summation j equals to 1 to k uj mu j minus half summation I j both running from 1 to k ui uj sigma ij. Now, this right hand side is nothing but the characteristic function of multivariate normal distribution. So, by uniqueness theorem, x follows multivariate normal, and naturally the converse can be proved similarly. So, you see here we have used this Cramer-Wald device in order to prove the multivariate normal distribution, prove the CLT with respect to a multivariate normal distribution. Now, just to give a feel, let us consider a concrete example. Let u1, u2, u1n, u2n, u3n, they follow the exponential distribution with mean theta, and for the sake of simplicity, here we assume that all u1n, u2n, u3n, they are actually IID distributed, or that means independently and identically distributed random variables for n equals to 1, 2 and so on. But these are all univariate random variables. Now, from here we will first define a proper multivariate distribution of a sequence of random vectors, and then we will see how the convergence can occur. So, in this case, let us define x1n equals to u1n, x2n equals to u1n plus u2n. So, it is clear that x1 and x2 are not uncorrelated. Basically, u1n is common in both x1 and x2n. Similarly, we define x3n equals to u1n plus u2n plus u3n. So, it is clear that u1 is common in all three variables, u1 plus u2 is common in x2n and x3n. So, that really generates or creates a correlation structure among the random variables x1n, x2n and x3n. In fact, we can derive that it is extremely easy to evaluate that expectation of x1n equals to theta, because x1n is nothing but u1n and u1 is nothing but an exponential distribution with mean theta. Expectation of x2n is 2 theta, expectation of x3n is 3 theta. Variance of x1n is theta square, variance of x2n is 2 theta square, and variance of x3n is 3 theta square. Similarly, we can evaluate covariance between x1n and x2n, which is same as covariance between x1n and x3n, and which is in fact nothing but theta square, and covariance between x2n and x3n is equals to 2 theta square. So, it is clear that since theta is greater than 0, there is a proper correlation structure among the variables x1n, x2n and x3n. So, we can safely say that x1n, x2n and x3n together forms a vector, a random vector, and which is a proper multivariate distribution with a proper correlation structure. There is no question of independence among x1, x2 and x3 random variables or the components. So, x1n, x2n, x3n follow a multivariate distribution with a correlation structure. So, we define y1n as x1 bar minus expectation of x1n by sigma 1 by root n, y2n as exactly similarly like y1n with respect to x2 bar, and y3 is same as y2n or y1n, except that it is a function of x3n bar. This is nothing but basically standardized version of x1, x2, x3n. Now, we can consider y1n, y2n and y3n as an univariate sequence of random variables. So, we can apply univariate CLT to each of these sequences, so that we see that yjn converges in law to yj, j equals to 1, 2, 3, where yj follows normal 0, 1. Now, I will show by random generation or simulation, I will show the histogram of this random variables, which is seen to be normal 0, 1. So, that might give us the confidence that actually this can happen. But it is clear that again y1, y2, y3 are not independent, because we can calculate the correlation between them, and since the variance of each of them is 1, then covariance is nothing but the correlation, which is in fact covariance between y1 and y2 is 1 by root 2, or that between y1 and y3 is 1 by root 3, and that between y2 and y3 as root over 2 by 3. So, we might think that y1, y2, y3 prime jointly follow a multivariate normal distribution with mean vector 0, 0, 0 and a variance covariance matrix sigma, where sigma takes this kind of structure. Here just for the sake of calculation, 1 by root 2 is nothing but 0.707, 1 by root 3 is nothing but 0.577, and square root of 2 by 3 is 0.816. So, I have written in this way because when I did this calculation, I get the decimal values in decimal points. So, now we shall show the simulation results to get a feel of what we have studied till now. Now, here is the but before that, the simulation plan goes like this. First, we generate data from u1n, u2n and u3n, then construct data for x1n, x2n, x3n from u1n, u2n, u3n by considering their relationship. Now, generate y1n, y2n, y3n from x1n, x2n, x3n values. Repeat the above procedures to get samples for y1, y2, y3, as the y1 and y2n, y3n converges to y1, y2, y3 respectively. That we can immediately obtain by applying univariate CLT to each of the sequences separately. Now, we will, to ensure that what we are getting is correct, we will draw histograms and also do Kolmogorov-Smirnov test to check normality for each of these y 1, y 2, y 3. Now, up to this is fine, because we can assure about the convergence of univariate random variables y 1, y 2, y n, or actually the sequence of univariate random variables which are y 1 n, y 2 n, y 3 n. But how to ensure the multivariate normality? One easy way to choose various values of L, that means L 1, L 2, L 3, to see whether L prime y follows a univariate normal distribution with appropriate mean and variance. So, if we can show this thing for many choices of L without putting any particular relationship between L 1, L 2 and L 3, then we might be confident that yes, this multivariate normality holds in this case as per Cramer-Wald device. So, here for the sake of demonstration we have considered only one, but this can be treated as a good exercise, that just try with several choices of L 1, L 2, L 3 and see whether L prime y follows a univariate normal distribution with appropriate mean and variance. Now, if we look at the histogram of this top left corner, which is the histogram of y 1, this is pretty good. It is a pretty close to the normal distribution, and the Ks p value means Kolmogorov-Smirnov test gives us the p value 0.783. That means H naught of H naught, that means the normal distribution or the standard normal distribution and assumption is true, or actually y 1 follows standard normal distribution. That is ensured by this p value based on Kolmogorov-Smirnov test. Similarly, in the top right corner gives us the histogram of y 2, and again Ks p value is 0.585, ensures that y 2, the component y 2 is nothing but standard normal distribution. This exactly same thing can be observed in case of histogram with respect to y 3. Now, here in the last diagram, which is bottom right corner, we produce the quantile plot for a set of values that is generated from by taking L 1 equals to 1, L 2 equals to 1 and L 3 equals to 1. Here we have given only particular choice, and it is seen that it actually, this red line falls on almost on top of this dotted black line. That means it actually follows univariate normal distribution with appropriate mean and variance. Now, we can try with many other choices of L 1, L 2, L 3, and I am sure we will see that the same kind of picture we will be able to see. So, this ensures that, or gives us a confidence using simulations we can try, we can check whether Cramer-Wald device is actually holds in any example of a convergence with respect to a multivariate sequence of random vectors. Now, note that the way we constructed the multivariate vector is not basically from a particular or from a standard normal distribution, but from an exponential distribution, a positively skewed distribution. And but again, by defining the random vectors and looking at the large sample properties of the distributional convergence properties, we see that it follows multivariate normal distribution, and that is seen using Cramer-Wald device. Now, we will state another version of multivariate CLT, which is called multivariate version of Lindbergh CLT. Lindbergh CLT for univariate random variable is known to us. Let us assume that x1, x2, xn be independent k-dimensional random vectors with certain mean vector as 0 and dispersion matrix as sigma I. Sigma is definitely a positive definite matrix, and define Sn equals to x1 plus x2 plus xn. Now, if we see that 1 by n summation I equals to 1 to n capital sigma I goes or converges to capital sigma, which is a non-null matrix, and for every epsilon greater than 0, this condition holds true, that is summation 1 by n summation I equals to 1 to n integration over norm of x. In case of univariate, this was mod of x, but since we are dealing with multivariate distribution or random vectors, we have to consider norm of x. greater than equals to epsilon into root n, then norm of x square d f I goes to 0 as n goes to infinity. Of course, capital F I is the distribution function of capital X I vector, and norm of x is the standard Euclidean norm. Under this condition, it can be easily shown that S n, the vector sum of the random vectors divided by square root of n, convergence in distribution to a k dimensional normal vector, k dimensional normal distribution with mean 0 and dispersion matrix capital sigma. Just as an outline of the proof, we will use Cramer-Weld device. So, transform the vectors to variables using Cramer-Weld device, apply Lindbergh CLT for univariate random variables to these random variables or these transformed random variables, find the limiting variables using this CLT, then apply Cramer-Weld device to get back the limiting vector. So, just a repeated application of Cramer-Weld device will prove the Lindbergh stability theorem with the help of Lindbergh's CLT for univariate random variables. So, here we have used these facts, Cramer-Weld device we have used, Lindbergh's CLT we have to use, and also the continuity theorem of characteristic function, because inbuilt there is always this characteristic continuity theorem of characteristic function that we have always used. So, as already discussed, this multivariate central limit theorem has a close connection with the univariate central limit theorem. In fact, the characterization of multivariate central limit theorem is using the central limit theorem for univariate sequence of random variables. We have also seen that this famous theorem and along with the proof, which is called Cramer-Weld device. We have also given one concrete example, and we have some feeling, because when we studied the simulations with respect to the convergence and with respect to the multivariate CLT. So, this gives us an idea or a complete picture of central limit theorem for a sequence of random variables or random vectors in this case, but most importantly here we assume that the sequence of random vectors are also independent. So, this actually concludes one important chapter in probability which relates to central limit theorem.